Okay, good morning. Let's get started. We are going to finish lecture 7 today, looking at the first 2 experiments in evolutionary robotics. The first one using the small hockey puck Kepler robot on the tabletop race course. And what we saw there was an attempt to create a fitness function for a robot that would drive either forward or backward. We saw 2 things in that experiment. First is that we tried our best not to build in too many assumptions about the kind of behavior that we wanted. We could have asked the Kepler robot to drive forward as quickly as possible, turn away from obstacles on the left, turn to the left when there's obstacles on the right, and so on. We try to make as few assumptions as possible, which you'll see when we start to look at some more complex evolutionary robotics experiment is sort of the game that we're playing here. We would like to pose to the evolutionary algorithm what we want the robot to do, but not to tell the robot how to do it. The other thing we saw in the Kepler experiment was that evolution exploits various aspects of the opportunities and limitations of the machine itself. So the Kepler drove at max about 48 millimeters per second, which was evolution fine-tuning how fast it could get the robot to move given the refresh rate of the sensors, even though the top speed of the robot was faster. We'll finish today by discussing this strange gantry robot we saw that was created at the University of Sussex in the UK at about the same time as the Kepler experiments. Okay, any questions about the assignments? All good? Okay, so let's jump right back into lecture. Okay, so just to remind you, we're looking at this interesting gantry robot here, which can move in the X direction and the Y direction. So it has 2 motor neurons that are controlling those 2 trolleys. We have this third motor, which is spinning this dental mirror underneath the inverted periscope, but we're going to assume for today that it just sort of spins constantly. The robot's not really controlling that spin, but as that dental mirror spins, the downward-facing camera is then able to see 360 degrees around it, and we take that 360-degree view, change it to polar coordinates, and then the evolutionary process is able to apply these areas of foci. So it's actually looking at particular places, and evolution can decide where they are. So in this case, we're evolving not just the synaptic weights for the neural network that controls the robot, but we're also allowing evolution to evolve the eye for the robot itself. Where is it looking and how is it looking? So we've got 2 motors, X and Y. We have a total of 7 sensors. Whether the bump disc at the bottom is being bumped from front left, front right, back left, or bottom right, back right, 4 sensors, plus the average grayscale values coming from those 3 areas of focus in the visual field. 7 sensors, 2 motors. Okay, we ended last time by looking at an incremental approach to evolution. We're going to see this in a number of experiments throughout the course. Often the final thing that we want the robot to do is very difficult, and it becomes a needle in the haystack problem. Remember our discussion about fitness landscapes? A needle in the haystack problem is where there is some optimal or near optimal solution. There is some set of synaptic weights for our robot that will get it to do what we want, but it sits at the top of a very narrow mountain, and there are very few foothills leading up to that mountain, so it's going to be very unlikely for evolution to find that final optimal solution. So instead, we're going to use, in this case, 1, then 2, then 3 fitness functions, and every time we switch from one fitness function to the next, it's going to deform the fitness landscape. Remember that the height of any point of any one solution in the fitness landscape is dictated by the fitness function. So by definition, if we change the fitness function, we're deforming the fitness landscape. So the idea is we're going to try and get the robot near where this ultimate mountain is in the third and final fitness function. Then we're going to change the fitness function again, which is going to change the landscape and move the solutions closer to where that final solution might be. And then finally, with the third fitness function, we're altering the fitness landscape yet again. Hopefully the points are now close enough that they're on the slopes of that narrow mountain, which contains at the top the best possible solution to the problem. That's the idea of incremental evolutionary approaches. Okay, so we looked at the first fitness function last time, which is we're going to place a piece of black Bristol board at the back face underneath the table. We're going to take each neural network and evaluate it 4 times on the gantry robot. In each of those 4 conditions, we're going to move, or the trolleys are going to move the periscope to a particular initial condition, and then the neural network will take over, and the periscope will start moving, and the fitness function is simply how close it gets to the back wall. We'll assume the back wall is maximum y. Pretty straightforward. So we evolved for a while using this fitness function, and once we obtain a neural network in which, in each of the 4 trials, that neural network gets the periscope to move towards the back of the table, we are then going to cut the piece of Bristol board in half, and during those 4 trials, put it either back left or back right underneath the table. And we're now going to, in the second fitness function, measure when the robot stops moving, how close that inverted periscope is to the center of the back piece of Bristol board. So d sub I. You'll notice we have negative d sub I. Should be a sub I, it's just an I at the moment. Why negative? Not quite. We're penalizing distance. We're going to see a lot of fitness functions in this course, and ultimately all of them are some combination and permutation of rewards and punishments. So in this case, we are punishing any d sub I, right? We're dealing with the distance now, the distance from the final position of the periscope to the center of the black rectangle, and we want to try and minimize that distance. Simplest way to do is to make it negative. Right? So often you should be able to spot by parsing the fitness function whether we're trying to reward or maximize, in this case, d sub I, or penalize or minimize d sub I. Okay, pretty straightforward. So now we have, once we finish the second stage where we continue evolution on from stage 1, at the end of stage 2, we have finally, or the definition of the end of phase 2 is we finally evolved a neural network. When we place it in the robot 4 times at 4 different initial conditions, regardless of where the black rectangle is at the back of the table, it will always move towards the black rectangle. So we know that the neural network sees the black rectangle somehow and knows how to move towards it. We don't yet know how it's doing so. Once we get that, we move on to phase 3, where now we are going to try and minimize the distance from the final position of the turret to a black triangle and maximize the distance from a black rectangle. So we want to continue evolving these neural networks we obtained in stage 2 to now distinguish between different shapes. So now we have uppercase d sub I and lowercase d sub I. Uppercase d is the distance of either the rectangle or the triangle from the starting point, and the lowercase is the final distance. d1 is for the rectangle and d2 is for the triangle. So we've got this alpha term minus this beta term. Tell me about the beta term. What is it selecting for? What is its contribution to the fitness of a given neural network? Yes?
Influencing it to approach the triangle.
Exactly, right? So we want to try and minimize, the final distance to the triangle, which is lowercase d2, and maximize uppercase d2. Is that right?
Are you correcting for the distance that's moved? Like, are you subtracting the starting distances?
That's it. So we're looking for the difference here, right? So the initial distance from the rectangle and the triangle, and we're trying to maximize that difference. However close you are to the rectangle, maximize that as you move. And however close you initially are to the triangle, minimize that. Get closer to the triangle. Why alpha and beta? These are numbers that the investigators set on their own. What happens if you alter the values of alpha and beta?
Will favor either the triangle or the rectangle mode.
Exactly, right? So we can tune alpha and beta, which will increase or decrease selection pressure. So we're going to use this term throughout the course. Selection pressure is a metaphor. Obviously, there's no actual pressure, but it's the amount of force that evolution is pushing, the amount of harshness that evolution is placing on a particular behavior. So we can tune that up or down. If we set alpha or beta to 0, there's no selection pressure on moving towards or away from the triangle or rectangle, whichever of those terms we're zeroing out. So again, one of the things we'll see in a number of fitness functions is not only combining together multiple behaviors, go towards the triangle and away from the rectangle, but the amount of force or desire we want for those different behaviors. Evolution is always trying to strike a balance between these two things. It can clearly not maximize its distance from the rectangle, because as it moves towards the triangle, in a lot of cases, it's also getting a little bit closer to the rectangle. So evolution is trying to strike this balance between the multiple things we're asking it to do, and by playing around with weights on the fitness terms, we can sort of tell it how to strike that balance. Okay, that's a lot of lead up to this, which is what do these neural networks actually do? And I apologize for the quality of this image. I'll talk you through it. What we're seeing up here in the top are 4 placements of the best evolved neural network that was obtained from this experiment. So we're doing evolution with a population of neural networks over many, many generations. And right at the end, we look in the population at the end and we pull out the neural network that has the highest fitness. And we then take that neural network, download it back onto the gantry robot, and replay that neural network 4 times from 4 different starting positions. I'm sorry, 1, 2, 3, and 4. What is the gantry robot doing? Is this an optimal solution? Given those 4 initial conditions, this is the best thing that the robot could have done. Definitely not. Why not?
I mean, some of them are spinning. They're not going in a straight line.
We're getting this strange corkscrew type behavior instead of heading straight for the triangle. And even heading straight for the triangle might not be the best thing you can do, because as you move straight towards the triangle, you're also moving closer to the rectangle. The optimal path is probably some curved path where you curve away from the rectangle on your right-hand side and then zoom in on the triangle. But whatever the optimal solution is, this isn't it. But it clearly is a satisfactory solution. We asked the robot to go to the triangle and avoid the rectangle. Evolution is a satisficer, not an optimizer. What else can you tell me about this behavior? Why do you think it might be turning as it moves?
Could it be overfitting and just looking for the bigger and the smaller shapes?
Possibly. So
And
we
as
don't
you get
really
close
know.
to one shape, then you want to, it'll look bigger in the field, and then you move towards the other one.
Possibly. So it hasn't overfit, because I haven't shown you here, but if you move the triangle on the right side and the rectangle on the left, it will do this corkscrew pattern towards the right-hand triangle. So it hasn't really overfit. It actually does recognize, quote unquote, the triangle and move towards it.
Does that have something to do with the way it sees with the mirror, because the mirror is spinning?
It has something to do with the way it sees, absolutely. Remember that we're going to assume that the mirror underneath is spinning, but as the mirror is spinning, the whole periscope is also turning, which means that the overall field of view that it's seeing is moving. So we can sort of discount the spinning mirror. The spinning mirror just basically gives a 360-degree view, which is odd, which means the periscope shouldn't really have to corkscrew, because as it's moving, it can see 360 degrees all around it, including the triangle and the rectangle. So the corkscrew behavior seems kind of odd. Let's see if we can figure it out. The clue to figuring this out is actually hidden in the neural network itself. Let's have a look at this. Here's our we have 2 inputs here, which correspond to the 2 visual fields, the 2 circles that you see down there. Remember that we allowed evolution to create 3 visual fields, these 3 circles. In this case, evolution has said, I don't need 3, I only need 2. So there is a third visual field, but there are no synapses going outward from that third visual field into the neural network itself. It's basically pruned those weights away and sort of thrown away those connections. We see there are a number of synapses that flow from the left and the right down to the left motor and the right motor down here. We see some dotted lines here and some solid lines. What do you think dotted and solid lines represent?
Positive and negative.
Mm-hmm. Positive and negative weights or excitatory and inhibitory connections. We see most of these are feed-forward connections going from the input to the output layer. Here is 1, 2, 3, 4, 5 hidden neurons. Remember, those are the neurons that are sort of sandwiched in between the input and the output neurons. We also see some backward connections. We talked about that last week, these recurrent connections. You'll also see something new here, which are self-connections. This is a recurrent connection where it leaves a neuron and comes back to itself, which is a recurrent network, a recurrent connection. It's not flowing forward. What do the recurrent synapses give to the neural network? What added capability do recurrent connections allow?
Ability to base the next decision on the previous action.
Exactly, the ability to base your current action on the state of the neurons from before, right? So whatever the value of these neurons is here, it is flowing backwards into here and influencing these, and then they're flowing forward and so on. So it's basically evolving to remember, so there is some memory going on here. If evolution had not used these recurrent connections, if all we saw were forward connections, that would be a clue to us that evolution has solved this problem with no memory, doesn't need any memory, which in theory it doesn't, right? It sees 360 degrees, it can just look and say, there's the triangle, there's the rectangle, and off I go. Seems odd, right? This is kind of an anti-intuitive solution.
Is it because it's doing the corkscrew thing?
It's related to that. So we're going to put a few, there's a bunch of clues here. It's remembering something. It's using some memory. We've seen this corkscrew pattern. So it is somehow moving, and as it moves, because it's embodied, its visual field changes relative to its own self-motion. Not unlike I see all of your heads moving to the left when I move to the right. Right? So it's actively moving. It's evolved to do this. It's got this memory. Here's a third clue. Look at the actual placement of these two visual fields. There's one upper left and one bottom right. And again, let's take that overall circle and turn it upright. So remember, this robot is scanning 360 degrees horizontally. So it's looking from its point of view horizontally up to the left and down to the right as it corkscrews. And it remembers. Okay, let's try and put those three clues together. How does the robot distinguish between the triangle and the rectangle? Scott, do you have an idea?
The bottom corners, perhaps. 2 corners.
It's looking for corners or edges. It may not see those edges straight on, but it's using some timing information. So as the corkscrew is moving its visual field, and eventually one of those circles, because the circles are moving, it goes from a light patch to a dark patch, and it could be hitting the edge, the right-hand edge of either the rectangle or the triangle. There is no way for the robot to know. All it knows is that at a certain point in time, both the grayscale values in visual field 1 and 2 are both bright, and suddenly visual field 1 goes dark. It's seeing something, but it doesn't know what it is. What happens next is it continues its corkscrew. Let's imagine that it's moving and it's actually hit the right-hand edge of the rectangle. Keeps corkscrewing. What's going to happen at the next time step, or a short time later? One has gone dark, and then? The other one will go dark. When? How much time between 1 going dark and 2 going dark? don't really know. I haven't said much about what this actual corkscrew pattern is. Let's hold that for a moment. Let's assume that it continues moving past the rectangle, back into the white space between the triangle and the rectangle, and now visual field 1 hits the right-hand edge of the triangle, and again, visual field 1 goes dark. What's going to happen next as it continues the corkscrew?
It'll take a longer time for it to hit 2 because it's a triangle
Exactly.
than it will for the rectangle.
That's the key, right? The way in which this particular neural network distinguishes between triangles and rectangles is not just based directly on their shape, but based on a relationship between how it moves and what it remembers, because it has to remember when visual field 1 went dark, which is what those recurrent connections are for. And then the relative timing between the darkening of visual field 1 and 2 is how it distinguishes between triangles and rectangles. Exactly how it does that, you have to go down and look at the actual synaptic weights and the timing events, but I think you get the idea, right?
So did the researchers create all the synapses and then it just set the synaptic weights, or did it create its own synapses?
Good question. I didn't mention that. In this case, they allow evolution to also add and remove synapses as well as set the synaptic weights. Yeah, exactly. And we'll look at that again later in the course, where evolution is actually setting the architecture of the neural network by adding and removing synaptic weights or neurons. Okay. The reason we're spending so much time talking about this one evolved neural network is it's probably the greatest reminder in this whole course about why thinking about thinking is misleading. Right? This seems like a ridiculously simple task. Evolve a robot to distinguish between triangles and rectangles, and if it succeeds, which of course it will, because it's such a simple task, it'll probably do it the way we do. You look at the visual field and you see certain edges with certain angles between them and a certain amount of darkness. A rectangle has 4 edges and darkness in between. That is what a triangle and a rectangle is. This robot says, I don't know what you're talking about. The difference between a triangle and a rectangle is the relative timing of the darkening of my visual fields as I move in a corkscrew pattern. Both you and I and the robot can distinguish between triangles and rectangles, but the way we do it, at least the way we feel like we do it, seems completely different from the way the robot does it. Question?
So that loop right there, like, would allow for it to like remember how long it took for each individual shape?
Exactly, and we haven't gone into the detail, but if you can remember things with the right set of synaptic weights, you can also time things. So this is almost like a clock or a timer. If you think about a recurrent connection, let's look at a simple example. Let's say I have a neuron, and the neuron currently has a maximal positive value of 1, and it has a recurrent self connection of 0.5. Let's assume there's no activation function here and there's no other synapses. What's the value of this neuron at the next time step? 0.5, right? 1 times 0.5 is 0.5. At the next time step, 0.25. So you can see it's exponentially decaying towards 0. It's a bit of a timer, right? It's counting down from 1 towards 0. It'll never actually get to 0. But for our purposes, it's a clock. It's not a constant clock like we're used to, which is obviously how animals and humans time things. Again, thinking about thinking is misleading. You can do it with different kinds of timers, which is probably what's going on here, but a little more complicated than that. Scott?
Did it always corkscrew in the same direction, counterclockwise versus clockwise? Okay.
You can tell by looking. Does it always corkscrew in the same direction? Each of these little cartoons here, this is again, the position of the robot, the circle, and the little tail is the heading, the direction that it moved in the last time instant. So yes, it always corkscrews counterclockwise, right?
Some of them don't corkscrew. How did they find the way to the triangle?
Exactly, right? So even the explanation we've just gone through is, again, a first approximation for what's really going on. It doesn't clearly it doesn't need to always corkscrew. There is some curvature in here. In this case, there isn't even any. Hard to say, right? Probably this straight line motion is enough to sweep over the rectangle and the triangle a little bit, and enough for our purposes. In the case where it corkscrews multiple times, then visual field 1 and 2 darken multiple times. Hard to say. Does it need, well, it clearly doesn't need multiple times. It gets very complicated very quickly. Right? Again, a reminder that often these evolved solutions are often not optimal and also very difficult for us to understand.
So you said they allowed the neural network to develop with evolution.
Mm-hmm.
So in terms of what they set originally, did they design it with the loop first, or did it on its own create a loop?
The loop. Yeah, absolutely. They did not build in this corkscrew pattern. This is just something that evolution discovered. If we rewound the evolutionary tape, went back and redid this experiment again, starting in the first generation with another random collection of neural networks, and went through these 3 fitness functions again, do you think we would get the counterclockwise corkscrew relative darkening timing event trick? Who knows? Probably not. If there's one non-intuitive trick like this, there are probably lots of them. They may all be variations on the same thing or not. But what you can be certain of is that evolution is probably going to find a solution that exploits movement, may not be corkscrew movement, but some form of movement, timing, using remembering something, and also geometric constructions, placing the visual fields in different positions, right? We're bringing all of these pieces of embodiment together and allowing evolution to exploit them. Yes?
The reason it doesn't use blocks, so it's doing nothing, there's no objects in the box yet.
Yeah, I'm sorry. In this particular, they did multiple experiments with the gantry robot. This one that we're talking about today, they didn't use obstacles at all. Yeah. Question?
Does this totally break if you change the orientation of the triangle?
You mean for this particular evolved neural network?
Yep.
What do you think? So if we took the triangle and turned it upside down, think it would still work? Probably not, right? I'm assuming that it's tuned the timing here and the placement of these visual fields that it would say, I don't know what that object is, but it's not a triangle, right? We might see it as a triangle. It's an upside down triangle, but the robot may not.
But did it learn how to recognize a triangle, or did it learn how to recognize something that isn't a rectangle?
Ah, good question, right? So we're using the noun triangle for this thing, but again, we in the robot see it completely differently. So you could call it not rectangle if you want. It's a kind of an arbitrary term at the moment for this phenomenon. Who knows? What it is from the robot's point of view is something that causes 1 and 2 to darken at this relative timing when I corkscrew. That's what it is to the robot. Okay, let's carry on. So that's lecture 7 on the first 2 evolutionary robotics experiments, which illustrate some of the interesting things about this evolutionary approach, some challenges and some opportunities. Let's move on now and have a look at a pair of lectures under the heading of minimal cognition. As I mentioned last time, the idea here is to try and create a robot and a task environment that's as simple as possible. And then given that minimal cognition setup, we're going to carry out a number of experiments where we're evolving lots of different building blocks of intelligence. Can we get very, very simple organisms or simple agents to exhibit the different building blocks of intelligence? Before we talk about those in lecture 9, we're going to talk about a particular kind of neural network that was used for these experiments, which is definitely not minimal. It's a continuous time recurrent neural network. And unfortunately, to talk about CTRNNs, we're going to have to do a little bit of calculus. This is the only calculus you're going to see in this course, so bear with me. All right, back to high school. Y equals mx plus b. We have a straight line that has a particular slope, and that slope describes if we move a certain distance x, delta x. We also move along the line a certain distance y, the delta y. And the ratio between delta y and delta x gives us the slope, and then wherever that line hits the y is the y-intercept, right? all well and good, but what happens if we move an arbitrarily small distance along the x-axis? How can we describe our movement along the y-axis? As was discovered several hundred years ago, that becomes a little bit difficult. And an easy way to see this, at least for a computer scientist, is to write down not a differential equation, but a difference equation. In a difference equation, we are taking discrete jumps, and we want to know the new value of x at time t plus 1. We know the current value of x sub t, and in this case, for this particular slope, if we're taking big jumps, it's easy. We know if t goes from t to t plus 1, we're taking one big jump. If we move a smaller distance in time, t plus 0.5, we move a smaller distance in x. And as our distance between t and the next time instant becomes smaller and smaller and smaller, eventually when that becomes 0, x doesn't change at all, which doesn't seem to make sense. Things get a little bit funny. You'll notice here in this little cartoon example here, we're changing the amount of time that elapses from one time step to the next. The reason I put this in here is to remind you of our discussion about physics engines last week, right? We can change the amount of discrete time that occurs between one time step and the next. So this becomes very clunky to deal with, so eventually the calculus was introduced, and now we're going to describe things not as discrete steps in time, but continuous steps in time using dx over dt, which tells us how much x changes as a function of how much t changes. We're going to use the shorthand notation in a moment of x prime. So wherever we see a prime symbol, that's just a reminder that we're not dealing with the value of x, but we're describing how x changes over time continuously, right? So again, in this example here, if I want to describe continuous change here, I can do it using a differential equation, right? So to read this off, this says the rate of change of x is equal to the rate of change of dt. This ratio, the amount of change along t and along x, is 1. It's equal. All good? Should be pretty straightforward. Okay, let's apply this now to neural networks. Let's go back to the more familiar neural networks that we saw last time. We have a particular neuron. Let's assume we have a particular neuron called x, in this case, superscript 1, doesn't really matter. The new value of a neuron at t plus 1 is going to be some function of the other neurons that are feeding into it with synaptic weights based on their current values, right? We saw this, for example, it looks a little bit more familiar down here. X sub 1 at t plus 1, the new value of neuron x1 is the value of the weight leading from itself, from x1 back to x1, for example, plus the weight of some other neuron, x2, multiplied by the weight of the synapse that connects neuron 2 to neuron 1. That's the weighted sum that we're performing. We then take the activation function and squash that value to a new value that lies between 0 and 1, or minus 1 and plus 1, and that becomes the new value at time t plus 1 of the neuron x1, right? So in essence, we're using difference equations when we're computing a neural network. We're going to switch over now and start to build up the description of the behavior of a new neuron here, y sub I, so the ith neuron inside of a neural network. But the value of that neuron is going to change continuously rather than discretely from one time step to the next. So we're now going to be dealing with a continuous time neural network. The recurrent in there is a reminder that these CTRNNs are also going to have some recurrent connections. So let's try and draw this geometrically to build up an intuition about how a continuous time neuron operates. We're going to have time on the horizontal axis here, and we're going to have the value of y sub I. We're just going to plot how the value of one neuron in this neural network changes, how the ith neuron changes in this neural network. We're going to assume that the value of the neuron can range between -1 and +1 over time. In a continuous time neural network, in order to integrate or actually compute how the value of this neuron is changing over time, we're going to have to set some initial value for the neuron and then integrate forward in time from there. This is relatively straightforward to do. For all the hidden and motor neurons in the CTRNN, we're going to start by setting the value to 0. What is the initial value of the input neurons in a CTRNN, or the sensor neurons? How do we know what the values of the sensor neurons are at T0? Not all of them are going to be 0, probably.
Are they all -1?
Not necessarily all -1. Where do the sensor neurons get their values from?
Alright, they're randomly assigned.
Sorry? They're not randomly assigned.
Oh, wait, it's sensors. They get from the stimuli of the environment.
From their sensors, right? So whatever when we turn on the neural network, the robot opens its eyes, quote unquote, right? When it opens up its sensors, and those sensors start reporting values, which become the initial values of the sensor neurons. So suddenly we have initial values for all the neurons in our CTRNN, 0 values for the hidden neurons and motor neurons, because we haven't started computing the neural network yet. But we do have possibly non-zero values for the sensor neurons, right? Okay, so we're in good shape. We have initial values for all the neurons. Now we need to try and figure out how do the values of those neurons change as we move forward in time continuously. Okay, what we're going to do in this exercise is gradually build up an equation that describes how y sub I changes over time. So if you're following along by annotating your notes, leave the same sort of spacing that I have here because we're going to fill this in as we go. Okay, so we're going to basically introduce a series of increasingly complex differential equations that describe how y sub I changes over time. We're going to start with just one term, minus y sub I. So the rate of change of y sub I, which is y sub I prime, is equal to the negative of its current value. Seems kind of odd. Why would we start with that? What does that cause the neuron to do? Let's figure this out, build up an intuition by placing some hypothetical initial value, like, for example, y sub I, the initial value equals 0. If we integrate this forward, what's the value of y sub I at any point going into the future? 0, right? Y sub I prime equals 0, negative 0, right? The rate of change of y sub I does not change. It's 0, right? So if an initial neuron has a value of 0, just with this equation alone, it's going to be unchanging over time. What happens if we're dealing with a neuron that has a positive value, greater than 0? How is its value going to change as we move forward in time, as we start to integrate the neuron values of this neural network? It's going to decrease, right? And depending on our integration step, which we're going to sort of ignore at this point, we'll just say at some point in the future, it's going to decrease. So it's decayed to this value of 0.9. What is its value going to be as we continue to move forward from this instant in time? What can you tell me about the change in the value?
Still towards 0, but a lesser change.
A lesser change, right? So now y sub I prime equals minus 0.9. The rate of decay at this time is now less. It will decay towards 0, but never reach it, right? Approach it asymptotically. How about an initial value for y sub I of minus 1? How is the value of this neuron going to change over time? You're all remembering your calculus now?
It's also going to approach 0.
It's also going to approach 0, right? So it's going to increase in value, but at a decreasing rate. So for any initial value of y sub I, if this is all that it's being influenced by, which is its own current value, it will decay towards 0. Why is this term in there? We're going to see that CTRNNs are a little bit more biologically realistic than some of the other neural networks you might have seen. And that particular term is representing a particular phenomenon seen in biological neurons. Any biologists here, neuroscientists? What's going on here? Yep.
The negative feedback loop?
It's a negative feedback loop. It's decaying towards zero. So the neurons in your nervous system, whenever they fire, whenever the neurons activate, it is very energy intensive. It requires a lot of ATP to do their work. So when a neuron in a biological nervous system does its work, when it sends along a signal, it rests. There's a period in which no matter what else anything is saying upstream, the neuron says, I'm out. I'm not doing anything for the next half a second or second and a half. I'm spent. I need to recharge my batteries. Then I will return. So we are basically, if the neuron, in this case, in our synthetic neurons here, in the absence of any other activity, if they are stimulated either positively or negatively, they will do their work, they will signal, but gradually they will get tired and eventually they'll stop signaling altogether. They will come back to a zero value. Okay. Let's add to this set of to this differential equation. We're going to add a new term now, tau sub I. You may not have seen a value placed on the left-hand side of a differential equation. This is just to make it easier to write. If you want, you can mentally divide both sides of the equation by tau sub I, and then we have y sub I prime equals minus y sub I divided by tau sub I. So really sort of the tau sub I is on the denominator on the right-hand side of the equation. Okay. Tau sub I, as the name says here, is a time constant, which has an influence, again, is now going to make the behavior of any given neuron a little bit more complex, depending on the value of tau sub I. So we're introducing now a parameter, not a variable. Our variable is y, the value of the neuron over time. In this case, tau sub I is not going to be changing over the lifetime of the neural network. It's a fixed parameter that someone or something is going to set in a moment. But for now, let's just play around and build up our intuition by setting this tau sub I to different values. Let's go back to setting our initial value of y sub I to +1. So we're going to assume that it's excited. It's got a positive value. And let's set tau sub I to a very large number, 1,000,000. Doesn't really matter. Tell me about how the value of y sub I now changes as we integrate forward in time.
Would it oscillate?
Possibly. We have a very large tau value.
Decay much more rapidly.
Decay much more rapidly. We're dealing with a very large value of tau sub I.
It's the opposite, it'll decay very slowly.
It'll decay very slowly, right? So tau sub I is a very large value. If you mentally divide and put it on the other side, we're dividing minus y sub I. We're dividing it by the denominator tau sub I, which is now a very large number. We're dividing by 1,000,000, which means the rate of decay is divided by 1,000,000, and the rate of decay becomes very, very slow. It'll take a very, very long time for this neuron to approach zero. Same thing, let's leave tau sub I equal to 1,000,000 and set the initial value of y sub I to -1. How does this behave with a very large tau value? Same way, right? We haven't changed tau, it's still 1,000,000, so we're going to increase towards zero, but at a very, very slow rate, right? Okay, let's go back to y sub I equals +1, and now let's set our tau value to a value very near zero, 10 to the -10, for example. Now, how is this neuron going to behave as we move forward in time? It's going to speed up. The rate of decay is going to be huge. It's going to plummet towards zero. And depending, again, on our integration step, it might actually oscillate. It might shoot past zero onto the other side. And now we have a tau sub I, again, still of 10 to the -10. What's this neuron going to do now? It says, uh-oh, I'm negative. Go back up, right? So we have a negative value on the other side there. It's going to shoot a negative value with the negative is a positive number divided by 10 to the -10, dividing by a very small number, up we go, right? And we could get something that does this, or even worse, something that does this, right? Again, depending on the integration step, it might come down and hug the line. Whatever the neuron does, it's changing, its rate of change is huge, right? So by changing tau, we can change the rate of response of the neuron to its current value. A good way to remember this is very large tau values give you Eeyore, am I spelling that right? Eeyore neurons. Remember Eeyore from the Winnie the Pooh stories? Eeyore's happy where he is, doesn't care what else is going on around him. He just does his thing slowly and steadily. He cannot be pushed. That's the Eeyore neuron. Neurons with very small tau values are Woody Allen neurons. Any slight disruption in their behavior and they go absolutely crazy at the slightest perturbation. Remember the Eeyore and Woody Allen neurons and you'll remember tau values. Okay. Why might we need tau values? Why are we introducing this? We'll see how tau values are useful in a moment. We'll look at an application of CTRNNs at the end of this lecture, but just hold on to this idea for a moment. As I mentioned, we're distinguishing now between variables and parameters. We have the variables, which are the y sub i's. We're looking at just one differential equation here, but remember that we have multiple differential equations. If we have a CTRNN that has 10 neurons in it, we have a set of 10 differential equations, right? One describing the rate of change of each of the 10 neurons in our 10 neuron neural network. The sub I is just to remind us that we're looking at the ith differential equation in this set of differential equations. If we have 100 neurons in our CTRNN, we have a set of 100 differential equations. We have these tau values, and these tau values have the subscript, again, sub I, which reminds us that the value of tau is associated with that y sub I. We could have a neural network that has 10 neurons in it, and each of those neurons has a different tau value. Some of the neurons have a very large tau value, which means they're Eeyore neurons. Some of the other neurons in the same neural network have very low magnitude time constants, which means they're Woody Allen neurons. We have a mixture of neurons in the same neural network that respond more fast, or more slow to their stimulation. That will become very useful, as we'll see in the application at the end of this lecture. Okay, let's carry on. We're now going to add an additional term here, which is a summation. This should look familiar to you by now. Up till this point, the only stimulation arriving at y sub I is itself. We have sort of this, you can imagine again this self connection we just had. But of course in a neural network, as the network implies, there's more than one neuron. They're wired up with synapses, and those synapses are causing one neuron to influence the value of another one. So at the ith neuron, we have a whole bunch of other neurons. So 1 to uppercase n. Uppercase n is going to represent the total number of neurons in our neural network. We're going to take all of the other neurons and multiply them by the synaptic weight, W sub ji, which is a reminder that that weight is a single number, it's still a parameter, and it represents the weight of influence of neuron j on neuron I. So we're performing a weighted sum here, and when we perform that weighted sum, we have a single value, the value of that weighted sum. We add it to minus y sub I, and that entire single number dictates the rate of change of y sub I after we divide by the tau value. So far, so good? Okay, so y sub I is being influenced by itself, y sub I, and all the other y sub j's, and the rate at which it's influenced is being dictated by tau sub I. So far, so good? Pretty familiar? All right, let's keep going. We're going to place our activation function now, represented by the sigma. We're going to place it inside the summation instead of outside. This is a little modification, and let's see what that does. Let's start with the activation function itself. We're going to take whatever the value is inside the activation function and squash it, in this case, using the tan h function, which will give us back a squashed value between what and what range, between what and what value. Remember your hyperbolic tangent? -1 and 1, right? So whatever is coming out the far side of our sigma function here is a value between 1 and -1, multiplied by the weight and onward to influencing the behavior of y sub I. Why are we placing the activation function inside the weighted sum rather than outside? The reason why is, remember that we're integrating the value of y sub I here. So the way to think about this is, inside the neuron, there is the raw value, y sub I. And that value, when we integrate, as we saw in even the cartoon here, that value may be all over the place, maybe much larger than 1 and much more negative than -1. But the moment we want that value inside the neuron to be broadcast outside the neuron, as its value starts to travel out of neuron J and into neuron I, at that moment when it leaves the neuron, then we're going to squash it. So this is just a little bit of algebraic manipulation here, which makes it easier for us to remember that when neurons are influencing one another, the moment its value leaves the neuron, it's between 1 and -1, guaranteed by the tan h function. When it's multiplied by yji, depending on what w is, that value could become much larger or much smaller than -1. And especially when we sum it up, that influence of this entire term may lie far beyond the range -1 to 1, which may cause the new value of the raw y sub I, again, to lie far outside that range. Doesn't matter if it's outside that range, as long as it stays inside the neuron. The moment it leaves, we're going to squash it. Question?
So, the minus y sub I here, that is not squashed between 0
It's
and
not
1.
squished, right? Exactly. So this could be minus 10.2, right? Who knows? Doesn't really matter for our purposes. The reason why we're doing this is, again, depending on how we integrate with more or less accuracy, these values can be sort of all over the place. It's hard to guarantee that everything is being kept between -1 and 1. So we're going to kind of be lazy here. We're going to let the integration method and step do whatever it does. Whatever happens inside the neuron, no problem, just do it. And then when it leaves the neuron, squash it to 1 and -1. Whenever we query the neuron for its value, we're going to get back something between -1 and 1. Yeah? Okay. Let's carry on. We're going to add yet another parameter, g sub j in this case. So we're introducing another parameter, but this parameter is now being associated with the j neurons. The single subscript reminds us that for every neuron in the neural network, there is also a g value. So every neuron has its own tau value and its own g value. And g is the gain of the neuron. And we can see that we're placing it inside the activation function, and it's influencing neuron J's influence on neuron I. Let's assume that the gain value is always positive. And as the name implies, you can think of gain as a knob. We can turn it up from 0 and make the gain louder and louder and louder. Why introduce a gain term? What does this do? Let's compare it to W for a moment. Let's take one single synaptic weight, WJI, which represents the one synaptic weight that connects neuron J to neuron I. If that single weight goes up from 0, if we turn up the knob of WJI, then of course the influence of J on I goes up. J starts yelling at I louder, right? If we turn W down, WJI down towards 0, then J yells softer and softer at I until J is not saying anything at all to I. As W reaches 0, J has no influence on I, right? So why the gain term?
Seems to be manipulating the activation function to threshold. If the gain term is higher, then the neuron would fire quickly.
Possibly. So as the gain value goes up, obviously the influence on Yj on everything else it's connected to goes up, which means the activation function is going to be larger and probably the rate of change is going to increase.
global gain, or just that one neuron is going to speak to all of the connected neurons?
Exactly. So the G associated with any given neuron is basically the overall volume of that neuron on every other neuron, modulated by WJI. As you're going to see in a moment, all of the parameters, and we've introduced 3 sets of parameters so far, the taus, the Ws, and the Gs, we're going to place those under evolutionary control. And everything we've talked about so far, only evolution has had access to. Now we're going to let evolution play with all of these different knobs. So by allowing evolution to play with the Gs, it makes it easier for evolution to turn up or turn down the volume of this neuron on everything else it's connected to. If evolution picks G sub j here and turns G sub j down to 0, what has evolution done to G? Sorry, to J.
Kill the neuron?
What's that?
Kill the neuron?
It's killed it. It's basically not there. Regardless of what the W's are coming out of J, J has no voice, no influence whatsoever. So there's a question about whether evolution can actually add and remove synapses or add and remove neurons. This makes it kind of easy for evolution to turn off or turn on different neurons. By turning W's down to 0, you remove that synapse, or evolution removes that synapse. By turning G down to 0, you remove that neuron. In theory, evolution could turn off neuron J by tuning down to 0 all the W's leaving J, but the probability that evolution would hit and be able to do that, assuming that it's useful to turn off neuron J, be very, very unlikely. It just makes it easier for evolution to play with the global influence of the neurons in the neural network. Okay, we're almost there. One more 4th set of parameters here, theta sub j. So the sub j again reminds us that the single subscript reminds us that there is 1 theta associated with each neuron in the neural network. And we're placing it inside the activation function. So it's influencing the outgoing value of neuron J as that value leaving J goes on to influence the rate of change of neuron I. Why theta?
Because you need to have a weight.
Let's assume that theta can be, in this case, negative or positive. Gain was always positive, it's just sort of the volume of that neuron. Theta can be negative or positive.
Is that a way to make like a negative or a positive connection?
Exactly, right? So if we have a negative theta, we're basically bringing the value of y sub j negative, right? Whatever the actual value of j is, in this case, for y sub I, it was always oscillating kind of around 0. By using theta, if we set, for example, a negative value of theta, we can cause a neuron, whatever that neuron does over time, to more or less approach theta. It's sort of the default value of the neuron. Instead of decaying to 0, it decays towards theta.
I'm a little bit confused as to why you wouldn't make that multiply by theta. Is that because you want to make it approach a certain value as opposed to inverting it?
Yeah, that's a good question. You could multiply by theta. I think it would still decay towards 0. You need to have this constant offset.
I was just going to say that addition causes the shift in the graph, right?
That's
like
right.
the vertical.
Exactly. I think that's the case. So by adding it, you're shifting the default resting value of the neuron to the value of theta, right? So by having a negative theta associated with a neuron, it's always kind of shouting from a negative value, more or less, again, depending on what else it's doing. A positive theta means it's always shouting or emitting a value around a positive. Now, again, depending on all the things that happen between J and I, that's going to have complex repercussions, but basically it's a positive or negatively valued neuron, changing the offset. Okay, last item we're going to add. This is terrible notation, but bear with us here. Uppercase I, subscript lowercase I. So the subscript I reminds us that this is this value is associated with the ith neuron. I sub I is only going to exist for the sensor neurons in the neural network, and I sub I is going to be set to 0 for the hidden and the motor neurons. I sub I, the value of I sub I for a given sensor neuron is the value of that sensor neuron's sensor. That's the connection to the outside world. So I misspoke at the beginning when I said the initial values of the sensor neurons are 0. They actually are set to 0, but then they're made non-zero by the incoming values of I sub I. Okay, so in your mind's eye, remember that we don't have just this one differential equation. We have n of the uppercase N of them for the uppercase N neurons in the neural network. A subset of those n differential equations have this I sub I term, and that value is set by whatever sensor that sensor neuron is attached to. If a sensor neuron is attached to a touch sensor, which is -1 when the touch sensor is not firing and +1 when the touch sensor is firing, then I sub I is going to flicker between -1 and 1 as the robot that has the CTRNN inside it does its thing. If, for example, I sub I is the angle of a joint sensor, a proprioceptive sensor, then obviously that value of I sub I is going to be the current angle of the joint, and it's going to vary it's going to vary continuously, again, as the robot does its thing. Sound good? Question?
So in case of a sensor neuron, when I sub I is 1, that means everything else is a backward connection coming into it from some, because I was expecting the sensor neuron to be the very first in the layer.
Yeah, this is a little strange. There's a typical way to draw a CTRNN, and I'm just going to do it for 3 neurons. The neurons in a CTRNN are usually drawn in a ring, and then every neuron is connected to every other neuron. So we have all those those WJIs, which are all the synapses, including Y sub II. So we have the self connections as well. So here we have a 3-neuron CTRNN. Let's assume that we have one sensor neuron, which is this one here. I'll write in S here to remind us that this is a sensor neuron. Let's assume we have just one hidden neuron, which is this neuron here, and we have one motor neuron, which is the one down here. Okay, so let's assume we have one sensor neuron, which is attached. I'll just draw this as a dotted line to remind us that this is not a synapse. This is just a transferal of a value from, for example, a touch sensor in the robot. The touch sensor equals -1 at a given point in time, which means the I sub I associated with the differential equation for this neuron is -1. Sometime later, as the robot moves, that touch sensor flips from -1 to +1. The object containing the touch sensor comes into contact with the ground. This value switches from -1 to +1, and the I sub I in the differential equation flips from -1 to +1. So I sub I represents the value of the sensor associated with that sensor neuron. This neuron and this neuron do not have any sensors associated with them, so I sub I is 0, or it's just not there. It doesn't really matter. In addition, everything is connected to everything else, unless evolution removes some of these synapses and even neurons by playing with the W's and the G's. If we have 100 neuron CTRNN, you can imagine a ring of these 100 neurons all interconnected. Any other questions about CTRNNs before we move on? Okay. Let's have a look at an application of a CTRNN. Obviously, these neural networks are more complex. These neural networks are more complex than standard neural networks, so they better justify their added complexity by making it easier for us to evolve behaviors for robots. We're going to look at a particular robot here, this small humanoid robot, and we'll watch a short video of this robot in action. As you can see, it's a little small humanoid robot. It's able to look at the block, and if it's doing what it's supposed to be doing, it can grasp the block and manipulate it in various ways. like this. It's getting some help from its friend here. Lift the block once, put it back down, lift the block twice, put it back down, lift the block a third time, and put it back down. Okay, so the teacher is moving the robot's arms through these actions, and we're not going to talk too much about the way in which this robot learns. We're going to just focus on the CTRNN, which is inside this robot. This robot has proprioceptive sensors inside of its arms, which report the angles of the joints inside of its arms. So what can you tell me about the values of those proprioceptive sensors as that robot just performed those actions?
Some of them went down
And then?
and then leveled off.
And then? They went down and then came back up as the robot lifted and then placed the object back down. What else happened? It did it 3 times, so it's going to oscillate. Is that 3 times? Yeah, good enough, right? It's going to feel its proprioceptive sensors oscillate 3 times. That's what it feels like from the robot's point of view to lift and put the object back down 3 times. We'll focus for the moment just on the proprioceptive sensation. It actually can see this block as well. There are additional visual sensors. We won't talk about those for a moment. Not the most sophisticated action you've ever seen, but this action is actually built up of 3 smaller, simpler actions, which is pick up and put back down. These simple building block or Lego bricks of action are known as motor primitives. One of the amazing things about animals as they evolve to move from point A to point B is clearly we don't come up with a particular motor pattern for every single step we take in the world. We learn how to take a step, which is a motor primitive. Once we figure out how to take a step and not fall over, we can start to put building blocks together in different ways. Then we can take those higher order building blocks like walking and running and combine them together. I can walk for a short period of time and then run. So I can hierarchically start to compose together motor primitives, learn simple actions and work out the kinks. For example, don't fall over or don't drop the object. And then once you've worked out how to do them, you can compose them together in lots of different ways. And thanks to the magic of combinatorial optimization, you can put things together in an almost infinite number of ways, which guards against overfitting. Once you get the building blocks of things worked out, it's easier to combine them to solve new problems than it is to memorize the solutions to new problems from scratch. Okay. Turns out with robots, it's very hard using traditional neural networks to teach them how to lift and put the block back down, and then teach them how to do that thing 3 times. The CTRNN, as we're going to see in a moment, helps with that problem. Okay, how does it do so? Here's, in the top left here, this is sort of a cartoon representation of what the robot goes through during training. It starts in the home position, so it always starts in the same initial condition, which means we always have more or less the same starting angles at the joints. And then the teacher will either guide the robot's arms through a series of motor primitives, or after a while the teacher will let go and the robot will do it on its own. Like, for example, start in the home position, reach for the object, lift it up and down 3 times like we just saw, and then go back to the home position. Or reach for the object, move the object left and right 3 times, then back to the home position. Grab the object and move it forward and back 3 times, back to the home position, and so forth. Okay, so we're going to try and teach it these different motor primitives and putting them together in different ways. Here is one way we might be able to do that. This is a sort of a visualization of a standard neural network. Imagine that in this standard neural network we have 3 separate subnetworks. They're not connected to one another. Each of those 3 small neural networks is going to be trained to produce up and down, which is the green squiggle, left and right, which is the blue squiggle, and forward and back, which is the red squiggle. So inside the robot's mind, it has 3 neural networks, and if any one of them is turned on by a gate, that gate is allowed to do its thing. So we have a 4th part to this overall neural network, which is a gating system, which basically says, subnetwork 1, you're in charge of the motors. Stop. Now motor 3, subnetwork 3, you're now in charge of the motors. Stop. Now 2, now 3, now 1, now 2, now 1, which would allow the robot to compose together arbitrary sequences of these motor primitives, depending on what we ask it to do. So far, so good. Where have we seen this gating mechanism before? We've seen it in a simpler form right towards the beginning of the course. We're allowing different parts of the neural network to seize control of the motors at different times. Where have we seen that before? If you remember all the way back to the beginning of the course, when we talked about the history of AI, in the 1980s, Rod Brooks introduced the subsumption architecture, the neural network that's running inside your Roomba at home. Clean the floors, move straight, unless I sense that I'm about to go over the edge of the top of the stairs. Suddenly, a different network seizes control of the Roomba, causing it to turn and head in the other direction. Once it does, that subnetwork lets go of the Roomba, and the normal floor cleaning subnetwork takes over again. That's the same thing that we see here. In the Roomba, it's corporate secret, so who knows, but there's probably 2 or maybe 3 of these subnetworks. In the case of our little cartoon guy here, he also has 3 subnetworks. What's the problem with this approach? It works. It lets us, or lets the robot arbitrarily compose sequences of motor primitives. There's a problem with this approach. Yep.
The subnetworks can't work together.
They can't work together, right? Only one is in charge at any one time. That's true.
If it receives stimuli to turn on multiple networks, it has to decide which one takes precedence.
Okay, so if there's some situation in which both are useful or it's not sure which one, how does it deal with that? So again, how do we combine in parallel motor primitives? That may be tricky. Other ideas?
You could learn it could create infinite of these neural networks, and then it would increase the amount of processing power that we need to decide between each of these.
Exactly, right? So as this robot learns more and more motor primitives, you're going to need more and more of these subnetworks. There's no good way yet to enumerate the different motor primitives that we learn as human beings over our developmental process, but it's definitely more than 3. Lots of simple actions that you can perform. You probably don't have in this limited space different subnetworks for leaving Voti 207 and leaving Voti 209 and leaving Perkins 101, and there's no room, right? We don't want to have too many specific subnetworks because it doesn't scale very well. So I'll introduce this idea and then we'll see it in more detail next Tuesday. In the case of the CTRNN, which is actually controlling the robot here, it has 2 subnetworks that you see down here. They have some synaptic weights connecting them, so they're partially connected, which is represented in the cartoon here by the partial overlap of these dotted ovals. The neurons that are in the left-hand subnetwork here, they're fast neurons. And the neurons that are over here in this other subnetwork are slow neurons. Given what you've just learned about CTRNNs, how do we make fast and slow neurons? Not quite the gain. The tau sub I. So we are going to manually set the taus in this subnetwork. We're not going to let evolution play with them. We're going to set them to a large value, which means they're Woody Allen neurons. And the neurons in the right-hand subnetwork, we're going to manually set their tau sub i's to be very small values near 0, which means they're going to be the Eeyore neurons. And the Eeyore neurons and the Woody Allen neurons are going to play together in a particular way, which will allow this robot to learn more and more motor primitives and put them together in more and more complex patterns without having to add more neurons. We'll see how that happens on Tuesday. You have a quiz due tonight. Carry on with your assignments. Have a good weekend, and I'll see you Tuesday.